you very much, everyone, for joining this presentation. It's my pleasure to introduce our speaker, and it's Kamron Kopecky. Kamron is a physics and chemistry major at UAB, a double major, and I've been very pleased with him working in my group. He has done very fantastic work, particularly this summer, and his work has been submitted for presentations at both the Gaseous Electronics Conference in October here in Huntsville, Alabama. It's a conference of the American Physical Society, and also he has submitted an abstract to the Materials Research Society for presentation in Boston in November. I'm very pleased with his performance. The abstract at the GEC has already been accepted. We are standing by for the outcome of the MRS submission. So I'd like to introduce his presentation. His talk today is on the growth of epitaxial continuous iron selenide thin films by laser-generated plasmas for advanced materials applications. Kamron, please take it away.
Yes, thank you. As Dr. Kumar said, my name is Kamron Kopecky, and I'm giving a talk on the growth of iron selenide epitaxial and continuous iron selenide thin films. Let's see if I can. There we go. So our main goal with this project was to grow an iron selenide and strontium titanate superlattice. So iron selenide has been shown to be a high temperature superconductor under high vacuum. The detriment of iron selenide, though, is that it easily oxidizes in atmospheric conditions. And so it is proposed to layer the iron selenide with strontium titanate in order to prevent this oxidation, as well as enhance the superconductivity of the film. And this is through proposed electron doping and electron phonon coupling. Now, these samples are grown through pulsed laser deposition, shown here, where a laser ablates a target and ignites plasma plume. And we placed a square Langmuir probe here in order to measure the ions of the materials in the plasma. And this is to prevent oxygen incorporation into the materials, as this oxygen incorporation from the strontium titanate may affect the iron selenide quality. And this is down here, this is the proposed layering form that we have. And here I'll show, these are ion probe measurements from the Langmuir probe, in which these are the normal current pulses we get from the ions hitting the probe. And this is the typical kinetic energy distributions for the iron selenide and strontium titanate species. So from there, we set out to show the epitaxial growth of superconducting iron selenide and the growth of homoepitaxial strontium titanate. From the theta to theta symmetric scan down here from our X-ray diffraction, we can see epitaxial iron selenide growth C-axis oriented, as well as strontium titanate growth and with respect to these substrate peaks, which is also C-axis oriented. And a bulk iron selenide film was shown to have a superconducting phase, as seen by the critical onset here on this resistance graph. And then from there, once we've shown that we have epitaxial superconducting iron selenide, we set to prove the homoepitaxial growth of strontium titanate, in which strontium titanate was grown with varying peak kinetic energy distributions for these ions and the plasma. And from these peak kinetic energies, we can determine the sharpness of the interface and the homoepitaxial nature of the growth. And here we can see at lower peak kinetic energy distributions, we have improved homoepitaxial growth, as there's less reflections indicating there's more correctly aligned strontium titanate growth. From there, we demonstrated a basic heterostructure of iron selenide and strontium titanate, where a theta 2 theta symmetric scan shows the iron selenide is still C-axis oriented and epitaxial, and the strontium titanate substrate peak shows epitaxial alignment of the strontium titanate on top of the iron selenide. And further analysis with reciprocal space mapping shows that the strontium titanate layer on top of the iron selenide is indeed epitaxial with respect to the substrate, and shows like minor broadening along these axes. And then from there, XPS depth profiling shows a sharp interface between the strontium titanate and iron selenide layers, where we can see this also through the XPS of the iron peaks, in which these iron peaks are consistent with literature values for no oxidation in the iron. From there, reciprocal space mapping of the 002 iron selenide peak confirms further epitaxial growth, as does the symmetric scans from the theta 2 theta. The thick iron selenide, the bulk iron selenide layers show a critical temperature onset at 8 Kelvin, which is consistent with literature values for bulk systems. And then reciprocal space mapping of the strontium titanate 002 and 113 peaks confirm that there is epitaxial growth of the strontium titanate on top of the iron selenide with respect to these substrate peaks down below. From there, we wanted to further study the transition into the superconducting phase for iron selenide. So we began the growth of iron selenide magnesium oxide heterostructures. And this is in order to further study through terahertz spectroscopy, in which MgO is optically clear in terahertz region. And so from this, we studied two different samples of where the plasma ions were off incidence, about 5 degrees off of the normal incidence of the plasma plume, and where the plasma ions were at normal incidence, in which the iron selenide layer on the magnesium oxide is C-axis oriented and epitaxial in both cases. And there is minor differences in the thickness of these layers through X-ray reflectivity. We can find the thickness from fitting these curves. But the major difference in these, the off incidence and the normal incidence, is the continuity of the film. So through scanning electron microscopy, we can see that at the off normal incidence at about 5 degrees off, you can see that these lighter squares are the iron selenide islands growing. And this is a larger scale for just to see these gaps that come between these islands. And so we can see that at the same growth methods for the off normal and normal incidence, we have a much more continuous layer where we can't really distinguish major or little minor islands around. There's more major groupings together. And from this, we can conclude that there is a more continuous layer in the normal incidence. And that would lead to a further study down the line of at the point at which these islands turn into a continuous layer. So in conclusion, we demonstrated through pulse laser deposition that we can grow strontium titanate homoepitaxially on its substrate, as well as grow superconducting iron selenide. And this is enabled obviously by the Langmuir probe I initially showed that helps us prevent the oxidation of the iron selenide. And iron selenide and strontium titanate heterostructures were demonstrated, where we could see the growth of epitaxial strontium titanate as well as epitaxial iron selenide with a crisp or sharp interference between them. So there is no mixing between the layers. And then we also demonstrated that the continuity of the films can vary based on the incidence of the plasma ions onto the substrate, and that this incidence will require further study to determine where the islands become continuous. And I would just like to acknowledge the ALPIP program, as well as their NSF EPSCoR track funding. Thank you very much.
I'd like to thank Kamron for this wonderful presentation. And in parting, I just want to mention that Kamron is actually using this work as a basis for his master's thesis. He actually has just been admitted. He's been admitted a few months ago. Now he will start in this fall in the master's program in physics. So he will build on this research to, this is actually the basis for his master's thesis research in our research intensive master's program. And this will actually be his launching point to even further pursuits toward the PhD in physics, which I understand he wishes to pursue. So congratulations, Kamron, and thank you for your presentation again.
Hi, my name is Flasny, and thank you for watching this video. Make sure to follow us on our social media at CPHUL on Facebook, LinkedIn, and Instagram. Bye!